Objective 3. Identify the real zeros of a polynomial function and their multiplicity. So the graph to the right shows a polynomial function with 4 x-intercepts. At the x-intercept, the graph must either cross the x-axis or touch the x-axis. Consequently, between consecutive x-intercepts, the graph is either above the x-axis or below the x-axis. So on this graph, we have our x-intercepts that are on the x-axis. At these x-intercepts, the graph either crosses straight through the x-intercept or it touches or bounces off of the x-intercept. And then between these x-intercepts, the graph is either above the x-axis or below the x-axis. If a polynomial function is factored completely, it is easy to locate the x-intercepts of the graph by solving the equation f of x equals 0 using the zero product property. For example, if f of x equals the quantity x minus 1 squared times the quantity x plus 3, the solutions to the equation f of x equals 0 are 1 and negative 3. That is, f of 1 equals 0 and f of 3 equals 0. And 1 and negative 3 are the x-intercepts of the graph f. Okay. So now let's define the real zero. If f is a function and r is a real number for which f of r equals 0, then r is called a real zero of f. So some equivalent statements to this are r is a real zero of a polynomial function f is the same thing as r is an x-intercept of the graph of f, which is the same thing as x minus r is a factor of f, and r is a root solution to the equation f of x equals 0. So if r is a real zero of the polynomial function, then r is also an x-intercept of the graph of f. And x minus r is a factor of f. And then r is a real solution to the equation. So I know 4 different statements meaning similar things, but it's going to help us in trying to graph polynomial functions. And then also identify its characteristics. So let's do an example. So we are going to find a polynomial function of degree 3 whose real zeros are negative 1, 2, and 3. So if my real zeros are negative 1, 2, and 3, I can then write these zeros as factors. And I know factors are written in the form x minus r. So my polynomial function, let's just give it f of x, is going to be x minus a negative 1, x minus 2, and x minus 3. I can simplify this a little bit to x plus 1, x minus 2, x minus 3. Okay? So that means if I have a 0 that's negative and I'm writing it as a factor, I'm going to change the sign. Okay? So any polynomial function of the form f of x equals a times x plus 1 times x minus 2 times x minus 3 where a is non-zero quantifies. All right. So let's use a graphing utility to graph the polynomial found in part A to verify our result. And in this part, we're just going to let a equal 1 for right now. All right, so let's graph. Okay, so I have my calculator. And we are going to graph our function. So let's go to y equals, and we'll put in x plus 1. Remember, we're letting a equal 1, x minus 2, and x minus 3. And we'll press enter to enter in our function, and then we'll press graph. And this is our graph. Now, if we were to change a to 2, does the value of a affect the zeros of f? So if I changed a to 2, what would happen? So I'm going to go to y2, and I am going to make a 2 this time, and then enter in the rest of my function. I want to know if changing a changes my zeros. It's minus 3. Enter that in. And I'm going to have both of them show on the screen. So my first function is going to be in blue. My second function is going to be in red, just so I know the difference. So let's graph both of those. And I see here that my graphs still cross the x-axis at the same points. So no, the value of a does not affect the zeros. All right, but it does affect the vertical stretch. So multiplying it by 2 stretched both of the minimum and the maximum values in my graph. So I had a vertical stretch. All right, that's pretty cool. So if when f is factored, the factor x minus r occurs more than once, then r is called a repeated or multiple real zero of f. So if x minus r power m is a factor of a polynomial f, and x minus r to the power m plus 1 is not a factor of f, then r is called a real zero of multiplicity m of f. Note that in other texts, the terms multiple root and root of multiplicity m might also be used. Okay, so in other words, our powers on our factors are going to tell us the multiplicity of our zero. Okay. And multiplicity is just the number of times its corresponding factor occurs. So if I have x plus 1 times x plus 1, then my multiplicity would be 2 because that factor appeared 2 times. So in this example, we're asked to identify the real zeros and their multiplicities. So we have our polynomial f of x, right? It is written in factored form. So we can identify our zeros from each factor. So we'll take our first factor, 6x cubed, and set it equal to 0. And so we'll get x cubed equals 0, and so x equals 0. Then we'll set our other factor, x minus equal to 0. And so x will equal 5. And then we have x plus 1/4 equal to 0. And so x will equal negative 1/4. And so those would be the 3 zeros for this polynomial. Remember, you write your function in factored form and then use the zero product property to find your real zeros. So let's complete our bullet points. So 0 is a real zero of multiplicity 3, because its power is 3, because the exponent on the factor of x is 3. 5 is a real zero of multiplicity 1, because the exponent on the factor x minus 5 is 1. Okay, so we don't necessarily put a 1 there, but there is 1 there because x minus 5 is 1 factor. And then negative 1/4 is a real zero of multiplicity 4, because the exponent on the factor x plus 1/4 is 4. Alrighty. So suppose that it is possible to completely factor a polynomial function and as a result locate all the x-intercepts of its graph, so the real zeros of the function. These x-intercepts then divide the x-axis into open intervals, and on each interval the graph of the polynomial is either above or below the x-axis over the entire interval. So as discussed previously, sometimes the graph crosses the x-axis and sometimes it touches the x-axis. So if R is a real zero of even multiplicity, numerically, the sign of f of x does not change from one side to the other side of R. So graphically, the graph of f touches the x-axis at R. If R is a real zero of odd multiplicity, numerically, the sign of f of x changes from one side to the other side. So y would be positive and then negative, or negative and then positive. So graphically, the graph of f crosses the x-axis at R. Okay. So now let's apply this knowledge to graphing polynomial functions. So we're going to consider this polynomial function f of x equals the quantity x minus 3 squared times x plus 4. We are first going to find the x and y intercepts of the graph of f, okay, because it's the intercepts that tell us our intervals. So let's first find our y-intercept. To find the y-intercept, we are going to evaluate our function at 0. So f of 0 equals 0 minus 3 squared times 0 plus 4. So then we'll have negative 3 squared times 4. 0 plus 4 again. That's right. 4. Okay. So that would be 9 times 4, which is 36. Okay. So this would give us a y-intercept of 0, 36. So when x is 0, our y-intercept is 36. Okay. Next, we'll find the x-intercept. And for the x-intercept, we're going to set f of x equal to 0. So we have 0 equals x minus 3 squared times x plus 4. So that means we can take each factor and set it equal to 0 to find the values of x. So x equals 3 and x equals negative 4. So our x-intercepts are 3, 0 and -4, 0. So we found the x-intercepts of our graph. All right. So now we're going to use the x-intercepts to find the intervals on which the graph of f is above the x-axis and the intervals on which the graph of f is below the x-axis. So we have our function f of x and we have our x-axis. The two dots here represent our x-intercepts because the x-intercepts divide the x-axis into the intervals that we're trying to evaluate. So our first interval is going to be from -infinity to -4. Second interval is -4 to 3. And our third interval is 3 to infinity. So to determine what the behavior is of f of x, we are going to choose a number in each interval and evaluate the function f of x at that number. Okay, so for my first interval, I'm going to choose -5. My second interval, I'll choose 1, and my third interval, I'll choose 4. I could have chosen 0 for my second interval, but I already know that value because 0, 36 is my y-intercept. Okay? So now I want to evaluate f at -5, evaluate f at 1, and evaluate f at 4. And I'm going to use my calculator to help me. All right, so let's go to y equals. I'm going to clear the previous functions we have. And I'm going to enter in my new functions. So x minus 3 squared, and then x plus 4, and enter that in. I'm now going to go to my table because my table is going to help me identify the values of f at these chosen numbers. So second graph. And so I need the y values for when x is -5, 1, and 4. So to get -5, I'm going to scroll up here to -5, and I see that -5 has a y of -64. 1 has a y value of 20, and 4 has a y value of 8. So I'm going to write these in my notes. So -64, 20, and 8. Okay. So now I can identify their location on the graph. So the point -5, -64 is going to be below the x-axis. The point 120 is going to be above the x-axis. And the point 48 will be above the x-axis. Okay? So the value here will be below, and then this will be above and above. Alrighty. So now we are going to locate other points on the graph and connect the points with a smooth continuous curve. So what we're going to do is first write out our functions so that we can use to help us. It's x minus 3 squared x plus 4. We're going to bring down our key points that we already know, like the y-intercept, the x-intercepts, which are 3, 0, and -4, 0. Then we have our points that we chose from the table above, -5, -64, 120, and 4, 8. Okay. Now you may want to get some other values because you want to make sure you have enough to show an accurate representation of your graph. So in getting back to our calculator, I might choose some values like 2, 6, or 5 and 36, -3 and 36, and maybe even -2 and 50, just to make sure that I have enough points to show an accurate representation of my graph. And when I do, I want my graph to look something like this. Obviously, it doesn't show everything, but we can match it to our graph to make sure that it matches, which we will do shortly. Okay? So let us add those values. So we had 2 and 6. 5 and 36, -3 and 36, and -2 and 56. Okay, so let's plot these points. So I'm going to plot my x-intercepts first. So I have -4 and 0, and I had 3 and 0. Then I have 0 and 36. Just going to do something around here. And then I have -5 and -64. Well, 64 is not on my graph, so that might be a little hard to plot. So let's plot another value. All right, so we're going to do 1 and 20. 1 and 20. And we're going to do, that was -1 and 20. 1 and 20 is over here. Good catch. All right. Then we're going to do 4 and 8. 8, let's put that here. Okay. And then we can do 2 and 6. So 2 and 6 is going to be somewhere about right here. And then 5 and 36. 5 and 36 over here. Then -3 and 36. -3, 36. And -2 and 56. 2 and 56. And so it's 50, so 56. So it'll be right here. And I believe our other one was -5 and -64. So if I were to put it up here, it would be way, 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 way down here. But it only goes to -20. So that's going to be hard to show. But if it were -5, 56, it would be way down here, just to help us visualize. Okay? All right, so now we can kind of see the flow of the graph, but I also wanted you to take note that x minus 3 has a 0, gives us a 0 of 3, and it has a multiplicity of 2. Since it has a multiplicity of 2, it's even, therefore it touches the graph, right? So 3, it touches, so that means there's going to be a little bounce here, okay? Now, x plus 4 gives us a 0 of -4, and it has an odd multiplicity because there's a power of 1. Therefore, it crosses at -4. So that's why our line is going to go like this. Okay. So now we can connect our dots. Okay, and we'll connect these. And let's go down here. All right. All right. And so now we have the graph of f of x, and we can verify this with our calculator. So what we're going to do is go into our window, and we want our window to match what we see here. So our x min is going to be -7. Our x max is going to be 10, so we'll leave that. All right. It goes by a scale of 1. We'll leave that. Our y minimum is going to be -20. Our y maximum is 60, and it's going by a scale of 10. So we'll enter that in. So now when I press graph, I should have a visualization of what is exactly on my screen, which it does. It matches, which is great. All righty, excellent. Okay, turning points. So the points at which a graph of a function changes direction are called turning points. Each turning point results in either a local maximum or a local minimum of f. The following theorem from calculus tells us the maximum number of turning points that the graph of a polynomial function can have. So if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. If the graph of a polynomial function f has n minus 1 turning points, then the degree of f is at least n. So graphing utilities can be used to locate turning points. For most polynomials, calculus is needed to find the n minus 1 turning points. So in this next example, we're asked which of the following graphs could be the graph of a polynomial function. And for those that could, list the real zeros and state the least degree of the polynomial could have. For those that could not, say why not. So remember, graphically for polynomials, they must be smooth and continuous. So if we're looking at A right off the cup, we know that this could not be a polynomial function because there is a gap. So this cannot be a polynomial because there is a gap at x equals 1. Okay, right here. There's a disconnection between our two parts. For B, we see here that there are no gaps, no cups, no right corners. So this could be a polynomial function because it's smooth and continuous from what we see. So this could be a polynomial because it is smooth and continuous. Okay. So because it's a polynomial function, our problem asks us to list the real zeros and to state the least degree the polynomial can have. Okay. So for our zeros, this is going to be where the graph crosses the x-axis. So that's going to be at the points -3, -1, and 1. That's what these points are. So our degree in order to find our degree, we're going to use the expression n minus 1. So n minus 1 equals 2. Okay, that's the number of turning points. There are 2 turning points. There's one right here, and there's one right here. That's where they change from increasing to decreasing. So to find the degree, we're going to set the number of turning points to n minus 1, where n is the degree. So to solve for n, we'll add 1 to both sides, and so n equals 3. So that means this polynomial is a degree of at least 3. Let's do 2 more. All right, C. Well, C here has a sharp corner. So this cannot be a polynomial because there is a corner at x equals 1. Now D, similar to B, is smooth and continuous. So this could be a polynomial because it is smooth and continuous. Since it is a polynomial, we can identify its zeros. The zeros are going to be where the x-intercepts are located. So the zeros of this function are going to be -3 and 0. To determine the degree of this polynomial, we're going to take n minus 1 and set it to the number of turning points. All right, so we have 1 turning point here, 1 turning point here, and another turning point here, so that's 3. So then n equals 4. So this is a polynomial that has a degree of at least 4. Alrighty. So now let's dive in a little bit into n behavior. So consider again the polynomial f of x equals x minus 3 squared times x plus 4. Okay, that was the previous function that we graphed. Expanding gives us the result f of x equals x cubed minus 2x squared minus 15x plus 36. To show that the graph of f resembles the graph of y equals x cubed, we're going to factor out an x cubed out of all of the terms. That results into f of x equals x cubed times 1 minus 2 divided by x minus 15 divided by x squared plus 36 divided by x cubed. For the large values of x, either positive or negative, the terms negative 2 over x, negative 15 over x squared, and 36 over x cubed are close to 0. So for large values of x, f of x is approximately x cubed. So the end behavior of the graph of a polynomial function f of x is the same as that of the graph of the power function y equals a sub n times x to the power n. So that is your leading term of your polynomial function. So based on this theorem and the discussion on power functions, the end behavior of a polynomial function can be one of 4 types illustrated below. So if your power is greater than or equal to 2, meaning it's even, and your leading coefficient is positive, your end behaviors are going to go to infinity. Right? So they're both going to go to infinity. If your power is greater than or equal to 2, so even and your leading coefficient is less than 0, so it's negative, then your end behaviors are going to go to negative infinity. Now, if you have an odd power and your leading term is positive, then you're going to have opposite signs starting at negative infinity going to positive infinity. And then if you have an odd power with a leading coefficient that is negative, you will be going to positive infinity and then negative infinity. Okay? Now, to show this in a different representation, I have a graph here. So depending on whether you have an odd degree or an even degree and what your sign is of your leading coefficient, you can then identify the end behavior of your graph. Okay, so if you have odd degree and a positive leading coefficient, then you have opposite going from negative infinity to positive infinity. If it's odd degree and a negative leading coefficient, then it's positive infinity to negative infinity. Even degree, positive leading coefficient, both sides are going to positive infinity. Even degree, negative leading coefficient, both sides going to negative infinity. Okay. So in this example, we're asked which of the following graphs could be the graph of f of x equals x to the fifth plus x cubed plus x squared minus 2x plus 3. Okay. Well, we can use the end behavior to help us identify which graph it could be. So we need to identify the power and we need to identify the leading coefficient. Okay, so our power is 5 and our leading coefficient is 1. Our power 5, which is our degree of the polynomial, is odd. Okay, so if we're looking at our chart up here, we're going to be looking in the odd category. Now, our leading coefficient is 1 and 1 is positive. Okay? So therefore, we now know what our end behavior could look like. And so we now need to eliminate the graphs that do not have this end behavior. Okay, so the first one does, this B also does, C also does, and D does not. So we know it's not D. Okay. Now the next step is to identify the number of turning points, okay? Because we know this polynomial will have at most n minus 1 turning points. Okay? So this is going to be similar to what we did on a previous problem, right? So we know that the degree is 5. Right? So the maximum number of turning points that it could have is at most 4. Okay. So in looking at A, B, and C, we need to identify which one has 4 turning points. So the first one has 1, 2, 3, 4. B has 1, 2, 3, 4. And C has 1, 2, 3, 4, 5, 6, 7, 8. Ooh, so we know it can't be C. Okay, so now we are left with A and B. Okay, so we did the end behavior, we did the turning points, so what's left? Well, what's left is going to be your y-intercept. So our y-intercept, remember, is going to be our constant term. And our constant term is 3. So this means that our graph is going to have the point 0, 3. So between A and B, which one crosses the y-axis at the point 0, 3? So it's me. So it wouldn't be A because this is a negative y value, whereas B, this is a positive y value. So A is eliminated, and we now have B as our final answer. Okay. So let's summarize this. The end behavior of f is the same as the power function y equals x to the fifth. The y-intercept of f is 3, and that's because f of 0 equals 3. The degree of f is 5, so the graph of f can have at most 4 turning points. All right. So we have looked at a lot when it comes to graphing polynomial functions. So let's conclude by bringing together all of the different things that we have learned in order to identify the polynomial function of this graph. Okay. So find a polynomial function whose graph is shown. Use the smallest degree possible. All right, so when you're given a graph and they're telling you to find your polynomial function, here are the steps I would take. The first thing that I would do is I would pull out all of the information that I can retrieve from my graph. The first being my x-intercepts. So my x-intercepts are -2, 0, 1, 0, and 3, 0. So that means my factors are going to be x plus 2, x minus 1, and x minus 3. Okay. I have 1, 2, 3 turning points. All my turning points are 3. So that means my polynomial is going to be a degree of at least 4. Okay. So now that I have pulled out the information that I need for now, let's identify some multiplicities. Okay, and since we want the smallest degree possible, we'll just use 1 for an odd multiplicity and 2 for an even multiplicity. Okay. So looking at my x-intercepts, I know that x equals -2 is 0, and this has a multiplicity of 1. How do I know that? Because it crosses the x-axis, because it's odd. X equals 1 is also going to have a multiplicity of 1 because it also crosses, the graph also crosses at that x. And then x equals 3 is going to have an even multiplicity. So we'll give it a multiplicity of 2. And that's because it bounces or it touches the x-axis at that x value. Okay? So now that I have this information, let's set up our function. Let's give it g of x. So g of x equals a times x plus 2 times x minus 1 times x minus 3 squared. Okay. All right. So that is our g of x. Well, we want to know what the function is. So we need to find a. How can we find a? Well, there was one thing that I haven't mentioned yet that is given to us in this graph, and that is the y-intercept. Okay? So the y-intercept tells us when g of x is evaluated at 0, it equals 3, which means that my constant of my function in expanded form equals 3. So knowing that, I can find a. So let's do that. So g of 0 equals 3. So that means 3 equals a times x plus 2 times, well, let's first write out g of x before I plug it in. How about that? Let's write out g of x, just so that it's a little clearer. That's a times x plus 2, x minus 1, x minus 3 squared. So now when I evaluate g at 0, g of 0 equals 3. So everywhere I see an x, I'm going to substitute 0. Now simplify the right-hand side. So that's 2 times negative 1 times negative 3 squared. And it's a times 2 times negative 1 times 9. That's negative 18. A equals 3. So I'm going to divide both sides by negative 18. And so this equals negative 1/6. So g of x equals negative 1/6 times x plus 2 times x minus 1 times x minus 3 squared. And this is in factored form. If I needed it in expanded form, then I would need to multiply all of this out. Awesome. I hope that was as much fun for you as it was for me. So in summary, graphing a polynomial function. The domain of a polynomial function is going to be the set of all real numbers. The degree of the polynomial function of f is going to be n. Your y-intercept is going to be your constant, so that's when f of 0 equals a sub 0. Your graph is smooth and continuous. Remember, it doesn't have any corners, no cups, no graphs. The maximum number of turning points is n minus 1, so your degree minus 1. At a real 0 of even multiplicity, the graph of f is going to touch the x-axis, so it's just going to touch it and bounce off. At a real 0 of odd multiplicity, the graph of f crosses the x-axis. Between real zeros, the graph of f is going to either be above the x-axis or below the x-axis. And for end behavior, for large absolute values of x, that is for large values of x, either positive or negative, the graph is going to resemble, well, the graph of f is going to resemble the graph of y equals your leading term. So a sub n times x to the power n. All right. Okay, and that concludes section 3.1.